Let's see about crystal field theory of coordination compounds. In the crystal field theory, we are considering about the electrostatic model, which the metal ligand bond is assumed to be a purely ionic in nature, and thereby the force of attraction between the metal and ligand should be electrostatic. And ligands are treated as a point charge in case of anion or point dipole in case of neutron molecules. The 5d orbitals in an isolated gaseous metal atom or ions have the same energy. And during this stage we call as a degeneracy. This degeneracy is maintained if the spherically symmetrical field of negative charge surround the metal atom or ions. However, when this negative field is due to the ligands, then it becomes asymmetrical and the degeneracy of the d orbital is lifted. That means there is a difference in the energies in between the d orbitals when the negative field is due to the ligands. So thereby, due to the difference of this d orbital energy, there should be splitting of the d orbitals. This pattern of splitting depends on the nature of the crystal field, and that we call as a crystal field splitting. This crystal field splitting will be discussed here in two ways. One is crystal field splitting in octahedral complex, or another one is crystal field splitting in tetrahedral coordination entities. Now we'll see about the crystal field splitting in octahedral coordination entities. In an octahedral coordination entities with 6 ligands surround the metal atoms or ions, and there will be a repulsion between the electron in the metal d orbitals and electron in the negative charge of the ligands. So this repulsion which is here in between the metal d electrons and negative charge of the ligands. Now this repulsion is more when metal of the d orbital is directed towards the ligand, when it is away from the ligands. So if the metal d orbital electrons are directed towards the ligand, then in this case the repulsion force is more. Whereas if the central metal atom d orbitals electrons are far away from the ligands, then this repulsive force is less. Thereby those which are oriented towards the ligands will have more energy, and those which are far away from the ligands will have less energy. Thus the dx square y square dz square orbital which points towards the axis along with the direction of the ligands will experience more repulsion and will rise the energy, whereas dx y dyz and dzx orbitals which are directed between the axes will be lower in energies relative to the average energies of the spherical crystal field. Thus the degeneracy of the orbitals has been removed due to the ligand electron and metal electron repulsion in case of octahedral complex to yield 3 orbitals of lower energy which we call as a T2z. Those which have lower energy, that is dxy, dyz and dzx will be called as a T2z, whereas dx square minus y square and dz square which have higher energy are called as a EG set. This splitting of the degenerate level due to the presence of the ligand in a definite geometry is called as a crystal field splitting. So what do you mean by crystal field splitting? This is one of the important question. So crystal field splitting means when the The orbital electrons are surrounded by ligands. During the time there should be a repulsion between the orbital electrons and ligands electrons, and due to this repulsive force, the degeneracy of the orbital electrons become removed, and hence two orbitals which we call as the x square minus y square and the z square, which comes towards the ligands, will have higher repulsion, whereas the xy, the yz, and the zx orbitals which is far away from the ligands will have lower energy. Those which have higher energy we call as a T2Z, whereas those which have higher energy we call as a EG. Thus, during these cases, the degeneracy of the orbitals becomes lifted. During the time the orbital have two energy level and thereby separate to each other. This process of separating the orbitals is what we call as a crystal field splitting. The energy required during this we call as a crystal field splitting energy, and which was represented by delta O. O means octahedral. Here, the energy of the two EG orbitals will increase by 3 by 5 of the delta O, whereas the 3 to G 3T to G will decrease by 2 by 5 of the octahedral. That means from the original energy, this T to G 3 orbitals will decrease by 2 by 5 of the delta O, whereas this dx square minus y square and dz square will increase by 3 by 5 of the delta O. The crystal field splitting, that is delta O, depends on the field produced by the ligands and charges on the metal ions. Some ligands are able to produce strong field, in which case the splitting will be larger. So if splitting is larger, then we have strong field ligands, whereas weak field ligands consequently result in a small splitting of the orbitals. In general, ligands can be arranged in a series in order to increasing field strength, that we call as a spectrochemical series. In an spectrochemical series, which you have seen a series here, I minus, which is less than Br minus, that is what Sn, Cn minus less than Cl less than S2 minus less than F minus, like this one, a sequence we get it, and this sequence we call as a spectrochemical series. So an spectrochemical series is the series of the ligands which are arranged in order of increasing field strength. So this is what the definition of your spectrochemical series. This was ordered in the board examination. It is experimentally determined series based on the absorption of light by complexes with different ligands. Let us assign electron of the d orbitals in the metal ion in an octahedral coordination entities. The single d electrons occupy one of the lower is T2Z orbitals in D2 and D3 electronic configurations. The d electrons occupy in the T2Z orbitals. Singly in accordance with the Hund's rule for the D4 ions. For the D4 ions, that means if it is of D4, then pairing will start. So two possible patterns of electron distribute arises. First one is the 4 electron could be either enter in the T2Z level and pair with an existing electrons. This is the first way of possibility of arranging electron. In the second way, of arranging electron is that in the second way, it could be avoid paying the price of the pairing energy by occupying the EG level, which of these possible occurs depends on the relative magnitude of the crystal field splitting delta O and pairing energy. That means either the 4 electron will enter in the EG or T2G will be decided by 3 factors. First factor is crystal field splitting, that is delta O, and another factor is pairing energy. And how it will goes will be discussed here in the next. Now let us see. If delta O is less than pairing energy P, the 4 electrons enter one of the EG orbital, giving the configuration T2G 3 times EG1. And ligand for which delta O is less than P is known as a weak field ligands and form a high spin complex. So you need to recall these 2 points. First one is, if delta O is less than P, the 4 electron will enter either of the EG orbitals, giving T2G3 and EG1. And during this case, the ligand's field is called as a weak field ligand, and the form is called as it will form as a high spin complex. If crystal field splitting energy delta O is greater than P, it will become more energetic and favor for the pairing of electrons. The 4 electron will occupy in the T2G orbitals. So you will get T2G4 EG0, and ligand which produce this effect is known as a strong field ligand and form a low spin complex. So which one will form low spin complex and which one will form high spin complex will be discussed here. Now we'll go to the crystal field splitting in tetrahedral coordination entities. Crystal field splitting in tetrahedral coordination entities. This is the picture. Here only the difference is that the 3 orbitals will go upward, and dz square and dx square minus y square, that is EG will be in the lower energy level, T2G will be in the higher energy level in case of tetrahedral coordination entities. In tetrahedral coordination entities formation, in tetrahedral coordination entities formation, the d orbital splitting is inverted and is smaller as compared to the octahedral splitting. For the same metal, the same ligands and metal ligand distance, it can be solved that delta T is equal to 4 by 9 of delta O. 4 by 9 of delta O. Consequently, the orbital splitting energies are not sufficiently large for the forcing pairing, and therefore low spin configurations are rarely observed in case of tetrahedral complex. So this is what about the crystal field splitting in tetrahedral complex. Actually, crystal field splitting in octahedral complex is very important for the exam, but not tetrahedral. For the tetrahedral, you can see the diagrams and try to understand it. Now we'll go to the color in the coordination compound. Color in the coordination compound. Generally, color arises due to the absorption of energy. So some absorption of the energies from the visible spectrum. So the light that emerges is no longer white. The color of the complex is complementary to that which is absorbed. Suppose if you have seen a black area, that means that from that black area the area does not reflect the light, then the area becomes black. If you have seen a substance as a blue, that means that out of seven color light in the presence in the white light, your remaining six colors are absorbed and only blue is returned, and thereby we have seen blue. Suppose 3-4 colors are absorbed, then the remainings are produced out of 7. So suppose 3 is absorbed, then 4 colors will produce. So by mixing 4 color, what is the color? That will be the color of the complex. So this color of the complex can be explained by crystal field theory. Now consider the complex hexa aqua titanium 3, which is violet in color, and this is an octahedral complex where the single electrons, that is Ti3 plus, is a 3D system in the metal d orbitals. Now this metal d orbital is in the T2Z level in the ground state. The next higher stable energy state available for the electron is in the EZ level. So to jump from T2Z to EZ, the electron absorbed light corresponds to the energy of the blue-green region, and it should excite electron from T2Z level to EZ level. So you will get T2Z 0 and EZ 1. Consequently, the complex appear blue in color. Consequently, the complex appear violet in color. The crystal field theory attribute the color of the coordination compound to the transition of the electrons. This is what we have learned here. In the absence of the ligand, crystal field splitting does not occurs, and hence the substance is in colorless. For example, removal of water from hexa aqua titanium 3 chloride on heating rendered it colorless. So if you remove water from this compound, you will get colorless. Similarly, anhydrous copper sulfate is of white, but if you put 5 times of water, it is in blue in color. The influence of the ligands on the color of the complex may be illustrated by considering your hexaaqua nickel 2 plus complex, which form when nickel 2 chloride is dissolved in water. If the didentate ligands, that is ethane 1,2 diamines, is progressively added in the molar ratio of En is to Ni, that is 1:1 or 2:1 or 3:1, the following series of reactions and the associated colors changes occur. So this is the first one. If you have taken NiH2O6 2 plus, that is green. If you added En ethylene diamine, then it comes to pale blue. Like this one, if you put your En in tetrahedral nickel 2 plus, then you will get your blue purple greens. Like this one, addition of these ligands will automatically changes the color of the complexes. Now let us see about the color of some gemstones, and this part is also important as it was already in the board exam. The color produced by the electronic transition within the orbitals of a transition metal ions occurs frequently in our everyday life. Ruby, which is of aluminum oxide containing 0.5 to 1% of chromium ions, which are randomly distributed in the position normally occupied by the aluminum 3 plus. And the chromium species is a octahedral chromium 3 plus complexes incorporated to the aluminum lattice, and the transition of this center gives rise to the color of your ruby. Like this one, in case of emerald, Cr3 plus has occupied octahedral site in the mineral beryllium, your triberyllium dialuminosilicates. The absorption band is seen in the ruby's shift to longer wavelength, and that longer wavelength is what we call as a yellow, red, and blue, causing emerald to transmit light in the green region. This is what about the crystal field splitting, and this crystal field splitting poses some important questions. Now we will see about the limitations of crystal field theory. Crystal field model is successfully in explaining the formation of structures, colors, and magnetic properties of the coordination compounds. However, for the assumption that ligands are point charges, it follows the anionic ligand should exert in the greatest splitting effect. The anionic ligands actually are found in the spectrochemical series, but it does not give an account of the covalent characters of the bonding between the ligands and the central metal atom. These are the weaknesses of your crystal field theory. Now next is bonding in metal carbonyl. So in the bonding we will not discuss too much. We will discuss about the structures. Otherwise you must recall that the bonding in between the metal carbonyl is a pi bonding, and we will see about these structures, which is very important for the exams. So structures of nickel tetracarbonyl. Carbonyl means that those compounds formed along with the metal and carbon monoxide that we call as a carbonyl. Nickel carbon monoxide have a tetrahedral structures, whereas trigonal bipyramidal structure in case of ferric tricarbonate. Pentacarbonyl, ferric pentacarbonyl. Like this one, CrCO6 will have octahedral structures, and whereas Mn2CO10 will have these structures. So you need to understand the structures. The bonding in between the metal carbonyl is this one. That means in between the carbon and metal we have a sigma bond and 2 pi bonds. So this is what about the metal carbonyl bonding. The metal carbon bond in metal carbonyl possesses both sigma and pi characters. The metal carbonyl sigma bonds are formed by the donation of the lone pair of electrons on the carbonyl carbon into a backend orbital of the metal, whereas metal carbon pi bonds is formed by the donation of pair of electrons from the filled orbital of the metal into the backend or antibonding orbitals of the carbon monoxide. That means if the pair of electrons are donated from carbonyl carbon to the backend d orbital of the metal, then it will form a sigma bond. And if the pair of electrons are donated from the filled the orbital of the metal to the carbonyl carbon of the carbon monoxide, then it will form pi bond. The metal into the ligands bonding create a synergic effect which strengthens the bond between the CO and the metal. This is what about the metal carbon bonding. Now next is about the stability of the coordination compound. Up to this is there. So stability is represented by here beta, and the sample is just like your equilibrium constant, which you have written in the class 11, that is product divided by your reactant concentration. So if the reactions occurs in many steps, then each step will have different k. Then k means solubility constant. So the total solubility constant should be given by this equation, k1 into k2 into k3 up to kn. This is the total. So these are the about the coordination compounds. Application and importance of coordination compound was already deleted for this year. Thank you. This is the end of this chapter.